Marine transport is without doubt the most energy-efficient way of moving goods around the globe, but it is still a significant source of atmospheric pollution. Many vapors created by tankers are harmful to the environment. Volatile organic compounds contribute to low-level ozone and, in sunlight, react with oxides of nitrogen to create photochemical smog. Oxides of nitrogen and sulfur from inert gas contribute to acid rain. Many crude oils contain high levels of hydrogen sulfide, a highly toxic, corrosive, and flammable gas. Together, they pose a serious threat to human health and the ecology of the planet. One major source of pollution is entirely avoidable. Worse still, it takes place when vessels are at their closest to human habitation. During loading and tank cleaning of tankers, vapors from cargo tanks are vented to the atmosphere. But such large volume discharges are now unacceptable. Vapor must be controlled. Since the 1990s, most crude and product carriers have been equipped with systems to return volatile organic compounds to shore-based vapor emission control, or VEC systems. In Europe and North America, facilities exist to recover and dispose of these gases. More are being built around the globe. MARPOL Annex 6 enables terminals or national authorities to demand compliance with standards for vapor emission control. In the United States, many coastal and Great Lakes states already require control of volatile organic compounds, or VOCs, from crude oil and oil product operations. These include loading, lightering, tank cleaning, and gas freeing. Vapor emission control allows vapors from oil or chemical tankers to be returned to shore in a closed system, and then either converted back into oil through adsorption or burned. It includes vapor from ballasting operations, gas freeing, and purging of tanks. MARPOL Annex 6 specifies that crude oil carriers must have an approved VOC management plan to minimize emissions throughout all cargo operations. It should identify best management practices and be supported by a training program that ensures these are followed. It must take into account any VOC reduction devices fitted to the vessel. In particular, the plan should aim to minimize gas release due to low pressure and high velocity flows, and from partial filling of tanks. Loading and discharge sequences should be planned to minimize the time taken filling or emptying tanks. A target pressure for tanks should be identified, and this should be as high as safely possible. This pressure should be maintained both during loading and discharging operations and while in transit. The plan should also consider the benefits of reducing venting by minimizing the use of added inert gas. In the case of crude oil washing, VOC emissions can be reduced by shortening its duration and by using closed-cycle washing wherever possible. The plan must identify a person responsible for implementation who is experienced in these operations on that vessel. There are many benefits to be gained from vapour emission control, such as reduced health risks to terminal employees and those living near the port. Some benefits are environmental, such as helping to slow global warming and acidification of our seas. There are safety benefits, with a reduced risk of fire and explosion. And there are financial benefits too. As much as 450 barrels of oil can be recovered from vapours given off during loading of light sweet crude to a medium-sized tanker. On shore, the system consists of the piping and terminal connections, either flexible piping or chicksands, a pumping facility, processing plant, storage and disposal facilities, and the control room. On the vessel, the vapour collection system consists of permanently installed piping on deck, with either branch lines from tanks joining a common main, or connected directly to the manifold. The system chosen depends on the number of grades carried and the segregation required. On a crude carrier, or one designed to carry unsegregated cargoes, there is likely to be one or two common mains. Where vapour collection systems utilize the inert gas or IG piping, there must be a means of isolating the IG system. On a chemical tanker, each tank may have its own vapour line. Some may have vapour connections at each tank and utilize short lengths of hose for connection. Where vapours may react together, they must be kept separate. All piping must be electrically bonded to the hull and be electrically continuous. Each system must have a drain-off at the lowest point. An isolation valve capable of manual operation should be provided at each vapour line connection, and its operating position should be easily identified. The vapour control manifold must also be clearly identified. The last metre of the manifold pipe must be coloured yellow with red bands and have the word vapour in black. The manifold flange must have a safety stud at the 12 o'clock position. Any reduction flanges must have a corresponding hole and a similar stud. The receiving terminal's chicksan or hose will have a similar colour scheme. If a flexible hose is used, US regulations state that it must have a bursting strength of not less than 25 pounds per square inch and be able to withstand a vacuum of 2 pounds per square inch without deformation or collapse. Deck pressure management is crucial during cargo transfer. PV valves and deck breakers are essential to safe operation of the system. The vapour flow capacity of each PV valve must be at least 125% of the maximum loading rate of each tank to take account of gas evolution and to prevent the pressure within the tank exceeding its design limits. Each tank must also have a vacuum venting system capable of preventing a vacuum whether created by withdrawal of cargo or vapour, that exceeds the maximum design vacuum of the tank. There is a mandatory requirement to have a pressure monitoring and alarm system in the vapour collection system. If there is a common line, it must have a pressure sensing device. The pressure indicator, together with high and low pressure alarms, must be both audible and visible where the cargo transfer is controlled. High and low pressure alarm settings must comply with MARPOL standards. For instance, where there is a common vapour collection system, the high pressure alarm must be set at or less than the lowest PV release setting in the cargo tank venting system. Low pressure alarms must be set at not less than atmospheric pressure for inerted tanks, and the vacuum release setting nearest to atmospheric pressure for non-inerted vessels. A secondary means of full flow venting must be provided to prevent over or under pressure if the primary venting system fails. Alternatively, pressure sensors must be fitted in each tank, with a monitoring and alarm system in the cargo control room, or the position from which cargo operations are controlled. Key limitations on loading and discharging rates will include the acceptable pressure drop in the VEC system and the pressure and vacuum release capability of each PV valve. In practice, to avoid uncontrolled venting of vapour, overpressure alarms should be set at no more than 90% of the lowest pressure relief valve setting in the cargo tank pressure release system. Of course, many vessels are fitted with dual alarm systems, with an initial low pressure alarm set at 150 mm water gauge. However, the lower low pressure alarms must be set at not less than 4 inches or 100 mm water gauge on inerted vessels, or the lowest vacuum relief valve setting on non-inerted vessels. As monitoring and alarm systems vary between chemical, product and crude oil tankers, it is essential that responsible crew have read and understood the vessel's vapour emission control manual. An engineer should be consulted whenever changing pressure settings for VEC. The risks from overfilling are substantial, so another important part of the safety system is the overfill alarm system. There must be a permanently installed, closed gauging ullage measuring system with readings visible in the point of control, normally the cargo room. There is normally a fixed overfill alarm set at 98% capacity and an adjustable high-level alarm. To comply with the United States Code of Federal Regulation, the high-level alarm must operate before the overfill alarm, but no lower than 95% of the tank capacity. There must be audible and visual alarm indicators visible both on the cargo deck and where the transfer operation is controlled. Alarm indicators on deck must be clearly marked. The overfill alarm system must be designed to come into operation should normal loading operations fail to stop the tank cargo levels exceeding the normal full condition. The alarm must allow sufficient time for the system to be shut down
Yes, sir. Can you stop?
before overfill takes place.
Okay, thank you.
If automatic systems are to be used, this must be agreed with the port and terminal operator in advance. All monitoring systems and alarms must be independent, intrinsically safe, and have test facilities.
Okay, overfill around, obtain starboard 95.
In particular, the overfill control system must be independent of the cargo gauging system. In the US, there are special requirements for controlling the vapor of cargoes with a high freezing point, with the potential to polymerize, and those with high vapor growth rates. Vapor emission control is a little more complex than standard cargo transfer operations, so the risk of something going wrong is greater. Each person in charge of transfer operations involving vapor emission control equipment should have completed a training program covering the vessel's specific systems and especially in the ship-shore communications required. It should include the purpose and principles of operation and provide an understanding of the equipment involved, its inspection and testing. The procedures involved should be covered in detail, and these should be included in the training manual. Pre-transfer activities, pipe connection sequences, startup, normal transfer operations, monitoring, and emergency procedures should all be covered. Training should include awareness of shoreside terminal systems and operations. It must cover the hazards involved in VEC operations. These include poor lineup of the vapor line leading to leaks or constriction, cross-connection of cargo and vapor lines, vapor line blockage from condensation, water carryover from the deck breaker, or tank overfill, PV valve failure, a communication failure leading to over or under extraction by shore pumps, excess loading rate, failure of monitoring and alarm systems. These can cause over and under pressurization of tanks. In addition, there is increased risk of explosion from vapor passing over condensate and generating static electricity. The vessel should maintain written procedures for VEC, including a line diagram of the vapor collection system, showing the location and purpose of all control and safety devices. It should also provide essential operating details, such as maximum transfer rates, pressure drop, alarm and relief settings, as well as full operating and emergency procedures. Communicate with the VEC facility at the terminal to make sure you understand their facilities and their requirements. It is likely the VEC terminal will request details of the vessel's status. These may include estimated time of arrival, the last cargo carried and the last port visited, the vessel's ballast condition and its maximum air draft, the number and size of vapor return manifold connections, the atmosphere in tanks, especially relating to inert gas, high hydrogen sulfide, benzene, or mercaptan levels. A team meeting with all officers and crew involved from the bridge, cargo room, engine room and deck will help bring out issues and ensure that everyone understands their role.
We will connect Vapour hose.
Checks should be carried out on all PV valves, line valves, tank gauges, pressure and overfill alarms, and wherever possible, these should be tested for correct operation.
Octane starboard 90% is working.
The vapor control manifold must be checked to ensure it is in good condition. Test tank atmospheres. If inerted, they must contain less than 8% oxygen, measured at 1 meter, and 50% of ullage. Levels of hydrogen sulfide and benzene should be monitored. Now is the time to check that all relevant documentation is in order. If calling at a US port, the vessel must have a US Coast Guard endorsement on its certificate of inspection. The oil transfer manual must cover the vapor collection system, and there must be an expanded declaration of inspection. All procedures must follow international safety guidelines for oil tankers and terminals. A risk assessment must be carried out before all special operations. If changes are made to routine procedures, these must also be assessed for risk. A planning meeting with shore staff is essential. It should establish initial and maximum loading rates.
So maximum transfer rate, you need?
250 cubics or 6 bar on the shoreline.
These must be limited by the cargo tank venting system and pressure drop calculations to avoid unplanned venting.
We have to do one stop for changing shore tank.
They should discuss control of the cargo transfer. Usually, this is controlled from shore. As the vessel's chief mate would normally control cargo operations, it is essential that pressure management processes are agreed in detail.
Then we do that.
They should also agree restrictions, such as not using the mast riser to reduce pressure, and establish that loading and vapor recovery rates can be balanced.
Terminal, Joe Cypress, ready check.
Check all communications with the shore terminal, deck, cargo room, engine room, and bridge.
Ano ba yung nasa tapat mo yun?
Test lines for correct setup. Drain water from vapor lines. Check bonding on any equipment to be used within the tank and on deck. Ensure all tank access hatches and vents are secured. Check that the inert gas system is isolated from the vapor system by the block valve after the deck seal. Ensure there is a detonation arrestor in place close to the terminal vapor connection. Unless equipped with a self-test and monitoring system, the overfill alarm system should be tested for each tank prior to loading. If in US waters, the expanded declaration of inspection must confirm the vapor system is lined up. Any hoses or chicksan arms are connected securely. An insulated or non-conductive hose is employed. Initial and maximum transfer rates have been agreed. Minimum and maximum operating pressures have been agreed. Alarms have been tested within 24 hours. The inert gas in tanks is less than 8% oxygen. The oxygen analyzer has been calibrated. And the IG manual covers VEC operations. With all the checks made, it is good practice to start loading slowly and gradually increase the rate in stages.
Terminal, Joe Cypress, we are ready to receive cargo. Pump at 60 cubic meters.
Yes, just like this is a perfect terminal. We can pump at slow rate, 60 cubic meters per hour.
Checks should be made for leaks both in the cargo manifold and the vapor emission control system. With the first foot or so in the tank and the inlet pipe well covered, it is wise to stop loading and check all cargo, monitoring and alarm systems.
Yes, sir.
Check all is in order at the shore terminal.
My manifold valve is fully open now. Can you start at slow rate?
Resume at a slow rate and increase to the maximum agreed loading rate in stages.
Joe Cypress, this is terminal.
Yes, Vapour terminal, this is Joe Cypress. Okay, increase gradually to maximum. Over.
During loading, tanks should remain sealed and not be opened for sampling or gauging. If manual ullage gauging or temperature sampling is to be undertaken, it is essential to use the vapor lock system. Oxygen levels, deck pressure and transfer rates should be monitored constantly. There should be periodic checks with the terminal to ensure that volumes compare. This helps ensure that there are no hidden leaks and lines are set up correctly.
Terminal, Joe Cypress, Joe Cypress.
Joe Cypress, this is terminal.
Sir, could you please slow down for your rate, sir, because I'm always stopping now.
Slow loading at 90% and leave sufficient space in tanks for line stripping. Non-inerted cargoes must be allowed to settle for 30 minutes before access for sampling. This is to allow any static charge to reduce to zero. All pressures must be checked regularly after loading. For cargo transfer between vessels, a closed vapor loop is created by transferring the atmosphere from the loading or service vessel to the discharging vessel. Normally, the service vessel is specially outfitted for this purpose. Both the discharging vessel and the service vessel must have an appropriate certificate of compliance or an endorsement on their tank vessel examination letter. If the discharging vessel is inert, the service vessel must also be inert. There must be an oxygen content analyzer on the vapor line of the service vessel within 3 meters of the connection. The associated alarms must operate in the cargo transfer control position of the service vessel. The oxygen alarm must be set at 8% or below. Vapor lines must be inerted prior to use, and an insulated flange or a non-conductive length of hose must be used for the vapor connection. Vapor emission control has many advantages. If managed properly, it is safer, with less risk of explosion from vented gases. It reduces the health risk to both ship's crews and shore-based personnel. It reduces the nuisance of smells to local populations. It can increase the amount of oil delivered. And it reduces the damage done to the environment. But some risks, such as those from over or under pressurization and static electricity, may be increased. Has electrical bonding been checked? Have the PV valves and mast risers been inspected? Is there information on the maximum loading rates for each type of cargo? Have the crew been trained in VEC operations? Is maintenance up to date? Have pressure and overfill alarms been set correctly? Finally, are all the checklists, manuals and records up to date? And are the crew familiar with them? The key to safety lies in preparation, training, maintenance, vigilance, and good communications. Only when all these are in place can the benefits of vapour emission control be realised.